So definitely want to thank the organizers for including us. I think this meeting has been really exciting. We're kind of new to the magnetics world, so we appreciate being included, and it's been a great learning experience. So thanks. So I want to start by thanking collaborators, particularly 2 postdocs at NIST who've led the work that I'm going to talk about today. And then importantly, a very important collaborator at Ohio State, Rolando Valdez Aguilar. He really has helped us get into the magnetics business. I'm going to talk about 2 papers today, and we had a number of authors on there, and just definitely want to recognize them and how helpful it's been. So just to give you a quick outline, I'm going to talk a little bit about magnetic materials and why they're so exciting, although I think we all know that or we wouldn't be at the conference. And then to give a little more on Raman. Obviously, Ken did a great job kind of saying how important Raman could be to these materials, and I'm going to just continue that a bit and then explain some of our unique capabilities. And then I'm going to go into 2 separate stories. One is on iron PS3, and the next will be on chromium triiodide. And both of these are very, very recent works. So as we know, in bulk magnetic van der Waals materials, there is a lot of excitement in the different spin arrangements that are possible, whether it's, of course, antiferromagnetic between the layers, antiferromagnetic within a layer, and the different ways that those spins can align. So there's a rich, obviously, magnetic landscape in van der Waals materials. And then with the, of course, discovery of the 2D magnetic materials by now Professor Gong, who's come to the University of Maryland. So we're happy to have him as a new neighbor. And he spoke earlier in the conference. And then Professor Xu at Washington. Both of their works have really got us all excited and fired up in this area. And we're following in the bandwagon and look forward to learning more from others. In this very nice review from Ken, sorry about that. In this very nice review from Ken, he was talking about how many different arrangements and potential applications there could be for these materials. And so we are excited to explore those, and we're interested in exploring them from kind of their fundamental properties. So we're not going to be talking about devices today. We're just going to be talking about some inherent properties of these materials. So again, just a very quick Raman 101. Just to remind people, because I'm not sure Raman is very widely used in this community, but essentially we use laser light to look at inelastically scattered light off samples. And from graphene to many of the other 2D materials, Raman has played a nice, important role in showing us additional information in those. Also, so just to give you an example of how a typical Raman spectra might look, we have Raman shift along X and then intensity along Y. This particular example is, again, from one of these 2D materials, rhenium disulfide, which has a plethora of photons. So it was quite exciting to assign. But the neat thing about Raman, of course, is that it's highly specific, non-destructive if done properly. I always like to put the caveat, it is quite easy to destruct this sample, but it can be done non-destructively. And then, of course, it's diffraction limited. So your spot size is on the order of a micron. Resolution can be under 500 nanometers. And then the rich information that Raman can tell you, particularly from 2D materials, everything from layer number to strain, as was mentioned. But today, I would like to tell you that magnetic ordering is also possible with Raman, and I'm going to give you 2 examples of that. So I'd like to tell you a little bit about our unique Raman capabilities. It has taken us years to construct this setup. I want to be honest. We've been working at this for a long time, and I feel like just this year, late last year, we're making good headway. So this setup allows us to collect Raman and PL. Normally, PL is not what we're looking for, but it is possible in this setup. And we can apply to the sample a magnetic field. 0 up to 9 Tesla. In both the Faraday, which means your sample AB is perpendicular to the field, or Voigt, where they're in parallel configuration. Our temperature range is down to 1.6, and we have low frequency capabilities. Just like Ken was showing, it is important to be able to see these low frequency phonons, or as we'll see, where magnons are often present. And we go down to 7 wave numbers. Now, many of you don't deal with wave numbers, so let me clarify. That can be less than 1 MeV. So there are even chances for Brillion scattering and Raman to overlap in some of those regions. Another important capability is polarization control. We'll talk a bit about that, but it's certainly an absolute requirement for us in Faraday configuration because our objective is inside the magnetic field. And the objective and the lenses themselves actually rotate the light going down and coming back up. We do work in 180 backscatter, just to clarify that point. The other unique thing that we bring to this discussion is resonance excitation. So with Raman, as you know, it's kind of a weak process. So if it's possible to enhance the Raman scatter through matching and absorption, that would be very desirable. Well, unless you burn the sample. But we do have many laser lines. We have tunable sources that really span the entire visible, from the 400s to nearly 900 wave numbers in excitation. We have both device transport for in operando characterization and spatial mapping capabilities, but both of those are in italics because while we have them, we have not optimized those two capabilities, but we're working on that and look forward to reporting news on that in the coming years. Also, I just wanted to say we're always looking for exciting and interesting samples that perhaps could, these capabilities could really enhance the science that we're able to see. As I mentioned, polarization is really important in Raman. It actually helps us to assign the different features that we see. So we have our incoming light and we have our scattered light. And we can vary the angle between those and get a polar plot, as you see here. Or we can keep those two angles the same and rotate that compared to the sample. And these two different angles allow us to fill in the matrix elements and enable us to assign the features that we're seeing. This is going to be very important a bit later when we talk about it, but it's just another strength of Raman spectroscopy. So now let's get into the two examples that I'd like to tell you about. The first, again, is from the XPS3 family. And I'm guessing we heard a lot about these particular structures from Professor Gong from Korea. Unfortunately, his talk was one of the 3 a.m. talks, so I missed it, I will confess. But his team has done a great deal of work with these structures, and so I'm going to certainly highlight his work, but talk about a little bit of our additional work on that. So one of the interesting things with all of this family, whether it's manganese, nickel, or iron PS3, is that they have the same crystal structure. And that really, when you look at the magnetic ion, is the hexagon structure from graphene. So we feel very comfortable with that. But what's interesting is that the spin structures are quite different. So, and of course, their anneal temperatures are different, even changing a factor of 2 between manganese and nickel in this case. But what we can see is that the spin structures are quite different. Even between the manganese and the nickel, as we're seeing here. But even further, the iron is quite different in the sense that you really have to double the unit cell to have enough atoms to explain the process there. So iron is what we're going to talk about going forward. Although I'd also like to say here, we have some beautiful data on MNP-SE3 as we're moving into the SE3 family and hope to talk about that soon as well. So here are some examples of temperature-dependent Raman. Here we're looking at the MNPS3 with the Néel temperature of near 78 degrees. Now, all of these spectra are below the Néel temperature, but you'll note we're not seeing a lot of change by eye. Of note, right now we're using excitation at 515 nanometers, a green laser. You'll see throughout the talk, we'll be switching different lasers. Again, that's one of the assets of our capability. Then if we have a look at the iron PS3, we're able to highlight quite a bit of difference in this low frequency region. Again, this had been seen by the Korean team. And here is the transition temperature at about 118, the Neal temperature transition. What you're able to see is a rather unstructured feature become quite sharp and able to resolve that feature as the temperature decreases. If we decrease the temperature even further, I'm sorry because my face is over this part of the spectra. We are able, here we go, we're able to see as we go from 135 down to 100, we're definitely resolving two features. What's interesting, if we look at DFT calculations spanning the Brillion zone, we see that there's really no features at gamma. So just to remind you, Raman is typically looking at phonons at gamma equals zero, at the zero angular momentum. There are opportunities to see other phonons, and that can come in with zone folding. And in this case, these two features that we're looking at called Psi1 and Psi2, we believe, in fact, that is what's happening. So just as a bit of a cartoon here, we believe that these K points are not folding in, but rather the M points do. And that's giving rise to these two features. Another interesting point I'd like to point out that at room temperature, we still see certainly some spectral weight at this feature. So we're looking into that and have now done high temperature measurements. And again, that's something to look forward to in the future. So as we cool down even further, remember that transition temperature, Neal temperature, was near 118. We begin to resolve two more features, such that if we blow up the 40K, we actually can now count 4 modes. So what we plot on this far right is the temperature dependence of all the regular phonons, as well as these 4 new features. You can definitely see the temperature dependence of Psi4 is quite different from any of the other phonons. So again, these two features cannot really be explained by the zone folding that we spoke of just a bit earlier. And with that Psi4 behavior being so rapidly changing with temperature, we thought perhaps it could be a Magnon, a spin wave. And there is a pretty easy way to see if it is a Magnon, and that is to put it in a magnetic field, where in this case, the magnetic field is perpendicular to the AB plane of the iron PSC3. If it is a Magnon, one would expect that the feature would split in magnetic field, and that splitting would happen at about a wave number per Tesla. So again, with our unique setup, we can do this. Here is an example of Psi4, and it's, again, the signal to noise is very small, but you can definitely see these two features being resolved. And at this up here, that's at 9 Tesla. So we did it both in the positive and negative with magnetic field and fit the lines, and it is shockingly good. So this was quite comforting that, in fact, this feature is a Magnon. Furthermore, we look at our neutron scattering data, not ours, data from the neutron scattering groups. And again, what's neat about complementary Raman and neutron scattering is the neutron scattering guys can see the entire Brillion zone. We, of course, are quite limited around angular momentum equals to 0, but that's also where their signal isn't as strong. So it's very complementary. But you'll see here, they saw what appears to be a Magnon at about 15 MeV. And if we just convert that simply, it's on the order of 120 wave numbers, which is where we see our feature. So we're quite confident that that is a Magnon. There was one thing, though, that had us a little perplexed in the beginning, and that is that in the literature, sorry about that, the Fleury and well-known papers and books, etc., said that for one Magnon scattering, we should only see it in cross polarization. Again, we've talked about polarization earlier and how important it is. So let's look at our data. So here we have theta equals 0, which is parallel, and theta equals 90, which is perpendicular. And we see psi4, I'm sorry, the label here, or the Magnon, in both configurations. So we were a little nervous about claiming vigorously it was a Magnon just because of that slight thing. But we were able to do, again, the full polar plot, and it is clear that this is a Magnon, again, due to the temperature response and the magnetic field response. And what we think is happening is that, that in this 2D feature, in this 2D limit, if you will, that this particular rigorous definition of what's permitted and not is really not valuable. That there, in fact, the paper as written is not incorrect. It was the way that the people had been using their interpreter. So let's summarize the iron PS3. So if it's an antiferromagnetic magnon, we will frequency shift with temperature. We would expect the frequency to split with applied magnetic field, and we expected neutron scattering. And sure enough, all three things occurred. And furthermore, we learned that perhaps the way we think about the Magnon polarization needs to be expanded a bit when it comes to the 2D limit. All right, let's move on to the chromium triiodide. And this paper just went online this week in Nature Communication. So I'd like to motivate why we looked at chromium triiodide, because everyone and their friends are looking at chromium triiodide. So it wasn't clear that we could add anything new until, as we're finishing up or working on our iron PS3, this paper came out where they identified two possible magnons in the chromium triiodide. What was interesting when we looked at their data was that, not in the intensity fact, but that the frequency versus temperature, remember ours had that dramatic drop off in our Magnon in the iron PS3. They really kind of saw a consistent frequency with temperature. And so that made us wonder. Furthermore, they used the again, the assignment that you can only see the Magnon in cross polarization as an assignment metric. And from our iron PS3 work, we thought that might not hold valid, again, in this 2D limit. Furthermore, the neutron scattering done on iron PS3 did not observe two Magnons at gamma at these two frequencies that they observed these two endpoints. So it just had us wondering and made us want to check. And again, it helped. We were hoping it would help strengthen what we were doing in the iron PS3. Of course, many of you know all about the chromium triiodide, but I just want to remind you that in the bulk case, there is a transition from monoclinic to rhombohedral in the bulk case. And then, of course, at about 60 Kelvin, we see it move all the way to the ferromagnetic case. Well, how does that change, or does it in the 2D limit? Obviously, from Professor Shu's work, in the few layer 1, 2, and 3, it definitely has antiferromagnetic stacking. And what we know is the rhombohedral is ferromagnetic, whereas the monoclinic is antiferromagnetic. So we know that, in fact, we're not always going through that transition. But the question is, how thick do samples have to be to not go through that transition? Meaning, where does bulk really take over? So we had a sample prepared, again, with our colleagues at Ohio State, covered or sandwiched with HBN. As everyone's discussed, this sample is so air sensitive, it's a mess. So we were really blessed to have our colleagues at Ohio State prepare this sample for us. And even at 10 layers, we were seeing evidence of the monoclinic phase. Again, what's very nice about Raman spectroscopy is lattice configurations are easily spotted most of the time. And in this case, we can definitely see using cross and parallel polarization that we do see evidence of both the AG and BG, and those are only permitted in the monoclinic phase. So even up to 10 layers, where we thought we might be in the bulk approximation, we are seeing monoclinic. Also of note, we see the P1 and P2, I'm calling them P for peak, because again, these are the features that were called out in the previous paper in the Nature communication I just mentioned that were referred to as magnons. So I'm just calling them peaks for now as we study what they are. So it's monoclinic for sure. And we observe those same features that they saw. So that's, and again, that paper from Michigan, they were looking at few layer as well. So again, just saying this 10 layer is behaving like few layer limit is was an interesting thing for us and a bit unexpected. So of course, what we learned was if we apply our magnetic field, we can split magnons and see them. So we turned up that magnetic field to 9 Tesla, and we saw some interesting things. First, we saw a low frequency feature that turned out to have already been seen by, again, our Ohio State colleagues as a ferromagnetic resonance. Yes, Raman can see FMR. What's interesting is it's very close to 0 without magnetic field. So the only way we can see it is by applying our magnetic field and again, watching it shift with field. This is only the positive side of the split feature. The negative side, of course, is beyond our capability to see that in low frequency. So this is, in fact, a magnon. What's interesting, though, is at 9 Tesla, we lost our features of the P1 and P2. They're just gone. However, we're still in the monoclinic phase. So also, our, again, neutron agrees with this very low frequency magnon seen at gamma at angular momentum equals 0. So we were confident about that feature. We were baffled as to where the P1 and P2 went. So we decided to go back to very low magnetic fields and begin a more patient and methodical test of the application of field. Of note, now we're using 633 as the excitation source, a red laser. That's because the signal increases at 633 because of a slight resonance. We were speaking of that earlier, so it is good to have a few laser lines. So what I'm showing here is a Raman shift along X, and I'm highlighting these two features, the P1 and the P2. We're going to start at 0 Tesla in the XY, or the cross configuration, and we're going to increase, sorry about that, we're going to increase the magnetic field. And this very top feature is in parallel at 0 field. And what you can see is a dramatic shift between the spectral weight in the P's, the P1 and the P2. That weight is getting shifted back to the A expected phonons. So we were quite surprised by that. Then we looked at the polarization, and this polar plot was really helpful for us. And so what we're seeing at 0 magnetic field versus 1 and 2 Tesla, there is a shift. So there is a phase transition happening of some sort where you can see this angle is on the order of 30 degrees. I will say also at 9 Tesla, we did not see this polarization change again. So we see the shift, and then above 2 Tesla, it sits at that same location all the way up to 9. So let's look here. What we're seeing, this false color plot is so lovely for most spectroscopists. This is quite exciting. So let's look at the ranges that we're seeing here. Also, I want to highlight something we refer to as X1. This is a spectral weight And we can't fully understand it. We're doing more work now to understand it, but in this published paper that you'll see in NatureCom, we say we don't fully understand it. So I just wanted to be honest there. But in these ranges, we see, for instance, from 0 to 0.6, nothing happens, 0.6 Tesla. And then from 0.7 to 0.8, we definitely see shifting in intensity in the X1 region and in the P2 region. Here we have a range 3 where, again, little's happening. Range 4, things go crazy. And again, that's only 1.4 Tesla to 1.6. And then in range 5, where we go to the final place. And once we hit about 2 Tesla, the spectra, again, do not change up to 9 Tesla. So at that time, of course, many of the Magneto-tunneling papers were coming out. And we thought, well, perhaps they hold the key to helping us explain what we're seeing with our phonons. Of course, they can see high resistance when it's in the antiferromagnetic configuration, and then low resistance when it's in the ferromagnetic configuration. And what they saw were real step functions at about 0.8 and 2 Tesla. And this particular sample, I believe this is Ken Fay Mock's work, but there were many papers done, were up to 40 nanometers. And we looked at our data, and sure enough, we also saw a bit of a step function at this, close to 0.8 and 2 Tesla. What's neat, of course, is that our sample, we believe these measurements are quite intrinsic. There were no contacts put down, no device fabrication, no polymers added, or things of that nature. So what we believe we're seeing with Raman optically is that that 0.8, 0.6 Tesla, we're seeing the spins flip that are surface. They're interacting with the HBN. Again, I mentioned that HBN is both on the bottom and on the top. So at our first kind of major thing, we're seeing surface spin flips. And then as we apply the magnetic field, it took up to about 1.6, we're able to flip the rest of the layers in this sample. So if those two features, the P1 and P2, were magnons, we would have expected to see a large frequency shift with temperature. We'd see a frequency shift and splitting with applied field, and they would have been experimentally seen in neutron scattering. And none of those things did we see. So we believe those two features are unlikely to be magnons or single magnon excitations. Instead, we believe that P1 and P2 are zone-folded phonons, much like we saw in the iron PS3. And that's because in chromium triiodide, when you go from the ferromagnetic to the antiferromagnetic case, again, your unit cell doubles. And so by doing so, again, you can see non-gamma point phonons with Raman. So here we have a beautiful theory from one of our colleagues at NIST, where he was able to predict the phonons for the antiferromagnetic and ferromagnetic case. And you can see that as you go from the ferromagnetic to the antiferromagnetic case, that those two P1 and P2 come in quite nicely and agree with what we're observing. So what we're excited about is that magnetic ordering allows us to see non-gamma point phonons. And that is exciting. And the idea that we can use both the phonons and the magnons to track the magnetic properties and lattice properties of these materials. So I hope that I'm able to convince you we finally have established our unique Raman capability to non-destructively probe phenomena in 2D magnets. And again, we're happy to discuss collaborations with people who think this technique might be of interest. In the iron PS3 case, we have corrected an assignment from a phonon to a magnon, and we also are beginning to understand this anomalous symmetry behavior for magnons. And then in the chromium case, it was exciting to see that Raman was very sensitive to the spin flip phase transition. The magnetic structure changes the symmetry of the modes, and that was quite exciting. And we corrected the assignment of a magnon back to a phonon. I definitely want to thank you all for your attention and for staying late today. I know we're a little later than the other days of the conference. And again, I want to thank my colleagues, particularly from Ohio State and NIST, Amber McCreary and Tuck May, our outstanding postdocs at NIST. So thank you all. I look forward to taking your questions.